At first glance, a galaxy seems to announce itself through light. There are stars gathered into spirals, pale lanes of gas, warmer clouds where new suns are forming, and sometimes a bright central region holding billions of stellar lives within a relatively small volume. Through a telescope, this luminous structure appears to be the galaxy. It has edges, shape, color, and motion. It seems complete. But the light is only the visible part of a much larger arrangement. Long before astronomers could map that arrangement clearly, they noticed a problem in the way galaxies move. Stars near the outer regions of a spiral galaxy travel around the center much faster than expected. If the gravity came only from the star's gas and dust we can see, those outer stars should move more slowly with increasing distance. Some should not remain bound at all. Instead, their speeds often stay surprisingly high across wide stretches of the galactic disk. Something appears to be supplying additional gravity. The same pattern emerges in galaxy clusters, where entire galaxies move through a shared gravitational environment. The visible matter does not seem sufficient to account for their motion. In other places, the light from distant objects bends more strongly than the luminous material in the foreground can explain. Again, gravity points toward mass that does not reveal itself through ordinary light. Astronomers call this unseen component dark matter. The name is simple, but it does not describe a single confirmed substance. Nor does it mean matter that is merely dim, hidden behind dust, or too far away to detect. Dark matter is a working scientific category for whatever produces these gravitational effects while remaining invisible to current forms of direct observation. It does not shine like a star. It does not glow like heated gas. It does not appear to reflect or absorb light in the familiar ways that ordinary matter does. We know it mainly by what it seems to do. Around a large galaxy, dark matter is thought to form an extended halo, much broader than the bright disk or elliptical body at the center. The stars you see may occupy only the inner luminous region of a gravitational structure reaching far beyond them. The familiar galaxy, from this perspective, is not the whole object. It is the bright interior of something larger. This changes the meaning of nearly every image of deep space. A spiral galaxy floating against a black background is not isolated in the simple way it appears. Its visible arms are moving within an unseen distribution of mass. A cluster glowing with thousands of galaxies may be held together mostly by matter that contributes no light of its own. Even the broad cosmic web, with galaxies arranged along immense filaments and gathered at their intersections, appears to have grown around a hidden gravitational framework. The universe has structure before it has brightness. Tonight, the path moves beneath the luminous surface of galaxies and into the evidence surrounding them. It will follow the motions of stars, the bending of distant light, the collisions of galaxy clusters, and the early universe itself. It will also remain close to the central uncertainty. Dark matter is strongly supported as a gravitational explanation, but its physical nature has not yet been identified, so the journey begins with a simple shift in attention. Rather than looking only at what shines, you can begin to notice what the shining things are responding to. A galaxy turns, its stars remain in orbit, and beneath their light, an unseen architecture holds its shape. There is another layer here, one that begins not with a new particle or a laboratory detector, but with the motion of galaxies themselves. In the early 20th century, astronomers were still learning how large the universe really was. Many objects once called spiral nebulae were being recognized as distant galaxies, each containing immense populations of stars. The sky had widened almost at once. What had seemed like a single island of stars had become a universe filled with many such islands, gathered into groups and clusters. One of the people studying those clusters was the Swiss astronomer Fritz Zwicky. In the 1930s, Zwicky examined the Coma cluster, a large gathering of galaxies hundreds of millions of light years away. He estimated how fast its galaxies were moving and compared those speeds with the amount of visible matter he could infer from their light. The result did not fit. The galaxies appeared to be moving too quickly. If the cluster contained only the matter revealed by starlight, its gravity should have been too weak to keep the whole system bound together over time. The galaxies should have escaped into surrounding space. Yet the cluster remained intact. Zwicky concluded that far more mass must be present than telescopes could see. He used a German phrase meaning dark matter. At the time, the idea did not transform astronomy. The measurements were difficult, the distances uncertain, and the amount of matter hidden in faint stars or diffuse gas was not yet well known. There were many reasons to be cautious. Zwicky's conclusion was striking, but it arrived before the observational tools needed to test it across many systems. For several decades, the missing mass problem remained at the edge of the field. Then, astronomers began measuring the rotation of spiral galaxies with greater precision. A spiral galaxy does not turn like a solid wheel. Stars and clouds at different distances from the center follow their own orbits, each responding to the gravity produced by all the matter inside and around them. In a simple system, where most of the mass is concentrated near the center, orbital speeds should decline with distance. The farther an object travels from the central mass, the more slowly it should orbit. This pattern appears clearly in the solar system. Mercury moves around the Sun much faster than Earth. Earth moves faster than Jupiter. Neptune, far from the Sun, takes nearly 165 years to complete a single orbit. The difference comes from the way the Sun's gravity weakens with distance, and from the fact that nearly all the solar system's mass is concentrated in the Sun itself. A galaxy is more complicated because its mass is spread through stars, gas, dust, and a dense central region. Even so, once an orbit lies beyond most of the visible to material, its speed should begin to fall. That is not what astronomers kept finding. In the outer regions of many spiral galaxies, stars and gas continued to move at nearly the same speed as material much closer to the center. When those speeds were plotted against distance, the expected downward curve often became almost flat. These measurements became especially persuasive through the work of Vera Rubin, Kent Ford, and other astronomers in the 1960s and 1970s. Using sensitive spectrographs, they measured the motion of gas and stars on opposite sides of spiral galaxies. One side was moving slightly toward Earth, shifting its light toward shorter wavelengths. The other side was moving away, shifting its light toward longer wavelengths. From those subtle changes in color, orbital speeds could be calculated. Galaxy after galaxy showed the same broad pattern. The visible disk ended, but the gravitational influence did not. The outer material moved as though it were enclosed within a much larger distribution of mass. The simplest picture was a halo. Unlike the thin, luminous disk of a spiral galaxy, this halo would extend in every direction, surrounding the galaxy with an approximately spherical cloud of unseen matter. It would be sparse compared with the density of stars near the center, yet so large that its total mass could outweigh all the visible matter in the galaxy. You would not see a boundary where the halo begins. There would be no dark wall, no surface, and no sharp air transition. The density would simply change with distance, becoming thinner farther from the center, while continuing well beyond the last bright spiral arm. The Sun itself would be moving inside such a halo. As Earth follows the Sun around the center of the Milky Way, the whole solar system passes through a region where dark matter is expected to exist. The amount near us would be extremely diffuse. A room, a mountain, or an entire planet would contain very little of it by mass, compared with ordinary matter. Yet across the full volume of a galactic halo, that faint contribution would accumulate into something dominant. This is one of the quiet reversals at the heart of the subject. The matter most familiar to us is concentrated. It gathers into bodies, oceans, atmospheres, stones, cells, and stars. Dark matter, if the standard picture is correct, is spread thinly across enormous distances. It does not need to be dense in any one place to control the motion of an entire galaxy. Its influence comes from scale. A single star responds only to the gravitational field around it. It does not know which portion of that field comes from other stars, which part comes from gas, and which part comes from matter that emits no light. Gravity carries no label. The orbit simply records the total. This is why rotation curves became so important. They turned invisible mass into a measurable pattern. The evidence was no longer confined to one distant cluster. It appeared across many galaxies in different environments with different sizes and different amounts of visible material. Some were broad spirals rich with stars. Others were faint, diffuse systems where the unseen components seemed even more dominant. The same question kept returning. How much matter is present and how much of it can light reveal? By the end of the 20th century, the answer had become difficult to avoid. The bright structures of galaxies were tracing only part of their own gravitational bodies. Around them lay a larger massed distribution, silent in every telescope designed only to collect light. The galaxy was not ending where the stars grew faint. Its deeper shape continued outward. Light does more than reveal distant objects. As it crosses the universe, it also records the shape of gravity along the way. This happens because space is not an empty stage through which light travels in perfectly straight lines. Despite, according to general relativity, matter and energy curve spacetime, and light follows that curved geometry. A massive object can therefore bend the path of light passing near it, changing the apparent position, shape, or brightness of something farther away. The effect is known as gravitational lensing. Unlike a glass lens, a gravitational lens has no polished surface. It may be a star, a galaxy, a cluster of galaxies, or an entire foreground structure spread across millions of light years. Its mass alters the region around it, and light from a more distant source follows the resulting curvature. If the alignment is close to perfect, a distant galaxy can appear as a luminous ring around the foreground mass. If the alignment is less exact, the same source may be stretched into arcs or divided into several images. More often, the distortion is so slight that it can be recognized only after astronomers measure the shapes of many background galaxies and look for a shared pattern. The important point is that light responds to total mass. It does not matter whether that mass is shining, cold, diffuse, hidden inside stars, or invisible to ordinary telescopes. Gravity bends light according to the full amount present. This makes gravitational lensing one of the most direct ways to map matter without depending on the matter's own brightness. A galaxy cluster is especially useful for this work. Clusters are among the largest gravitationally bound structures in the universe. They contain hundreds or sometimes thousands of galaxies, all moving within a common environment. Between those galaxies lies extremely hot gas, thin enough to seem almost empty by earthly standards, but spread across such a large volume that it can contain more ordinary matter than all the cluster's stars combined. That gas glows mainly in X-rays. When astronomers map the visible galaxies and the X-ray emitting gas, they can estimate where the ordinary matter is located. Then they study how the cluster bends the light of galaxies behind it. The resulting lensing map often shows far more mass than the stars and gas can explain. The cluster's brightest features are not its heaviest ones. Much of the gravitational weight appears to be distributed through a broad halo surrounding and permeating the visible structure. The pattern resembles what rotation curves suggest on the scale of individual galaxies. But here, the evidence spans a much larger region. Instead of tracking stars in orbit, astronomers watched the universe itself act as a measuring instrument. Background galaxies provide the light. The foreground cluster provides the gravity, and the distortions between them reveal where mass must be. There are two main forms of the effect. Strong gravitational lensing produces the most visible results. It creates arcs, rings, and repeated images that can sometimes be recognized directly in a telescope image. These shapes are not physical filaments attached to the foreground cluster. They are distorted views of more distant galaxies whose light has been redirected along several possible paths. A single background galaxy may appear more than once. Its images can arrive at different positions with different brightnesses because each path crosses a different part of the foreground gravitational field. The light may also take a slightly different amount of time to reach us along each route. In some systems, astronomers can use these delays to study both the lens and the expansion of the universe. Strong lens. Lensing tends to occur near the densest regions of a galaxy or cluster. Weak gravitational lensing is subtler and extends much farther outward. Most distant galaxies already have irregular shapes, so the distortion of any one object is difficult to recognize. But when many background galaxies in the same region appear to lean or stretch in a coordinated way, a statistical pattern emerges. Astronomers compare their orientations and measure the tiny changes produced by intervening mass. From this, they reconstruct a map. The map may show a central concentration around a galaxy cluster, long extensions between clusters, or halos surrounding individual galaxies. In wide surveys, weak lensing can trace matter across large portions of the sky, including regions where there is little visible structure. The universe begins to look different when seen this way. Ordinary photographs are organized by light. Bright stars dominate. Galaxies appear as glowing islands. Empty regions look black. A lensing map is organized by gravity. The brightest object may not correspond to the greatest concentration of mass. A dark region in an optical image may still contain a broad gravitational structure. What appears empty can influence the path of light, arriving from far beyond it. The word invisible becomes less complete here. Dark matter cannot be seen directly in these observations, but its distribution can be inferred through repeated effects. The evidence does not come from one bent ray of light or one unusual galaxy. It comes from patterns measured across thousands and eventually millions of sources. Each source contributes a small piece. Together they reveal a landscape. One of the clearest examples comes from clusters that have passed through one another. A cluster collision unfolds over immense periods. Two groups of galaxies approach under gravity, move through a shared region, and the galaxies themselves are separated by so much space that direct collisions between stars are rare. Most pass through the encounter with relatively little resistance. The hot gas behaves differently. Gas particles interact electromagnetically. As the gas from one cluster meets gas from the other, it slows, heats, and gathers near the central collision region. X-ray observations can show where this ordinary matter has been delayed. Gravitational lensing can then reveal where most of the total mass has gone. In several well-studied systems, including the cluster commonly known as the bullet cluster, the strongest lensing concentrations are offset from the brightest X-ray gas. The galaxies and the inferred dark matter have continued outward, while much of the ordinary gas remains closer to the center. The separation matters. If the missing mass was simply hidden, ordinary material mixed into the hot gas, the gravitational map would be expected to follow that gas more closely. Instead, most of the mass appears to move with the nearly collisionless galaxies rather than with the interacting plasma. This does not by itself identify what dark matter is. It does show that the dominant unseen mass behaves differently from ordinary hot gas during a cluster collision. It adds another independent line of evidence to the motions of galaxies and the rotation of stars. There are still careful questions. The reconstruction of a lensing map depends on models, distance estimates, image quality, and assumptions about the shapes of background galaxies. Cluster collisions are complex, and their geometry must be studied with precision. Astronomers compare observations with computer simulations to understand which distributions of matter can produce the measured patterns. No single image should be treated as the whole case. The strength comes from convergence. Galaxy rotation points toward additional mass. Cluster motions point toward additional mass. Gravitational lensing maps that mass across regions where light alone cannot account for it. Colliding clusters show that much of the mass can separate from ordinary gas. These methods are different. Their limitations are different. Their observations are made with different instruments and at different scales, yet they repeatedly lead toward the same broad picture. The visible universe sits inside a larger gravitational one. You can imagine the light from a remote galaxy beginning its journey billions of years ago. It crosses expanding space, passes through the curved environment of a foreground cluster, divides along several paths, and finally reaches a telescope near Earth. By then, the original galaxy may appear stretched into an arc. Its shape has become a message about matter it never touched. The background source tells us something about the foreground structure simply because its light traveled through the region. A distant glow becomes a tracing line, following contours that no eye could otherwise detect. This method has allowed astronomers to examine the outer regions of galactic halos as well. A foreground galaxy slightly distorts many fainter galaxies behind it. By averaging the effect around large numbers of foreground galaxies, researchers can estimate how far their dark matter halos extend and how mass is distributed within them. The bright disk may span tens of thousands of light years. The halo can reach much farther, gradually merging into the surrounding environment and sometimes overlapping with the halos of neighboring galaxies. There is no simple edge. The structure thins, joins larger group halos, and becomes part of the matter, connecting galaxies across broader scales. A galaxy is therefore not only a collection of stars moving through empty space. It is a luminous concentration inside a wider field. The field cannot be photographed in the ordinary sense, but it leaves signatures in every background galaxy whose light passes through it. Over enough distance, and with enough sources, those small distortions become a readable geometry. What looks like a scattered sky becomes a screen. What passes in front of it leaves a gravitational imprint. And across that screen, the hidden mass of the universe begins to draw its own outline. The evidence does not stop at galaxies and clusters. It reaches back to a time before either one existed. To understand why dark matter matters on the largest scales, it helps to imagine the early universe, not as a place filled with finished objects, but as a nearly uniform sea. There were no spiral arms, no mature stars, and no great clusters hanging in space. Matter was spread much more evenly, with only slight differences from one region to another. Those differences were small, but they were not meaningless. A region with a little more matter had a little more gravity. Over time, it could draw in material from its surroundings. As it gained mass, its gravitational pull grew stronger, allowing it to gather still more. In this way, tiny variations could become the first seeds of structure. The question is whether ordinary matter could have built the universe we see quickly enough on its own. For the first several 100,000 years after the beginning of cosmic expansion, ordinary matter was part of a hot, electrically charged plasma. Electrons moved freely, rather than remaining bound to atomic nuclei. Light scattered repeatedly from those charged particles, so photons could not travel far in a straight line. The universe was opaque. Ordinary matter and radiation were tightly linked. Gravity tried to compress denser regions, while the pressure of radiation pushed outward. The result was a pattern of compression and release, something like sound waves moving through the early plasma. Dark matter, in the standard cosmological picture, behaved differently. It responded to gravity, but it did not interact strongly with light. Radiation could not push it outward in the same way. While ordinary matter was still caught in the bright, pressurized plasma, dark matter could begin gathering around the earliest concentrations of mass. It could start building gravitational wells. Then, roughly 380,000 years after cosmic expansion began, the universe cooled enough for electrons to join with nuclei and form neutral atoms. Light stopped scattering so frequently and began traveling across space with far greater freedom. That early light still surrounds us today. Cosmic expansion has stretched its wavelengths into the microwave part of the spectrum, leaving a faint background glow arriving from every direction. It is called the cosmic microwave background, and it offers a view of the universe at the moment when light first began to move freely across great distances. The glow is remarkably even. Its temperature varies only by tiny amounts from one part of the sky to another. Those minute differences preserve a record of the density variations, motions, and pressure waves present in the early universe. They are not images of galaxies. They are the earlier pattern from which galaxies would eventually grow. Astronomers studied this background by mapping the microwave sky with instruments above much of Earth's atmosphere. The resulting maps may look mottled, with slightly warmer and cooler regions spread across the full sphere of the sky. The colors used in those maps are greatly exaggerated, so the differences can be seen. The actual variations are extremely small, yet the pattern is rich with information. Its characteristic scales depend on the contents and geometry of the universe. Ordinary matter affects the plasma in one way. Radiation affects it in another. Dark matter changes the depth of gravitational wells and the way early density patterns develop. When cosmologists compare the observed microwave background with mathematical models, a universe containing only ordinary matter does not reproduce the full pattern well. The standard model fits far better when it includes a larger amount of non-luminous matter that responds to gravity without remaining coupled to light. This is a very different kind of evidence from the orbit of a star. No single galaxy is being weighed. No foreground cluster is bending a visible arc. Instead, the composition of the universe is inferred from a background pattern formed before the first stars began to shine. The early plasma carried waves. Those waves left preferred scales in the distribution of matter. Long after the plasma disappeared, a faint statistical imprint remained in the spacing of galaxies. This feature is known as the baryon acoustic scale. The name can sound technical, but the idea is simple. Before atoms formed, pressure waves moved outward through ordinary matter and radiation. When the universe cooled and light separated from matter, the outward motion changed. The location reached by those waves became a slight preference in where matter later gathered. Billions of years afterward, astronomers can search large galaxy surveys for that preferred separation. It does not appear as a row of evenly spaced galaxies. It emerges only after the positions of enormous numbers of galaxies are compared statistically. Once again, the universe keeps a record. A pressure wave from the early plasma leaves a trace in the arrangement of galaxies across distances far larger than any one cluster. The pattern can be used to study cosmic expansion, but it also supports the broader picture in which ordinary matter falls into a gravitational framework influenced by dark matter. The visible web did not grow from ordinary matter acting alone. Computer simulations make this easier to follow. Cosmologists begin with density variations consistent with the microwave background. They represent matter in a large expanding volume and allow gravity to operate over cosmic time. In models with cold dark matter, slightly denser regions grow into knots and filaments. Smaller structures form first, then merge into larger halos. Gas flows into those halos, cools, and eventually forms stars and galaxies. The result is not a smooth universe. It becomes a web. Long filaments connect dense intersections. Galaxy clusters gather in the thickest nodes. Between the filaments lie broad underdense regions, the cosmic voids. Galaxies are not scattered at random. Their distribution reflects the growth of an older mass pattern. Here, the word cold does not refer to an ordinary temperature. It means that the dark matter was moving relatively slowly compared with the speed of light when structure began to form. This allows it to gather on smaller scales. A universe dominated by fast-moving dark matter would smooth away many early variations, making it harder to build the observed abundance of galaxies and clusters. The cold, dark matter model has been highly successful in reproducing the large-scale arrangement of the universe. That success does not mean every detail is settled. Simulations must also include ordinary gas, star formation, supernovae, radiation, black hole activity, and the many feedback processes that can move matter in and out of galaxies. On smaller scales, comparisons between models and observed galaxies can become complicated. Some differences may point to incomplete models of ordinary astrophysics. Others may offer clues about the behavior of dark matter itself. The broad pattern, however, remains persuasive. A largely invisible component begins gathering early. Ordinary matter later falls toward its gravitational concentrations. Stars form from gas inside those growing halos. Galaxies gather along filaments. Clusters emerge where the filaments meet. Light arrives after the framework has begun. There is a human tendency to think of the visible object as the primary one. A lamp seems more real than the room around it because the lamp announces itself. A city at night appears to be made from illuminated streets, while the unlit ground beneath them disappears from attention. Galaxies create a similar impression. Their stars outline spirals and elliptical forms, giving the eye something complete to recognize. Yet those bright patterns may be more like lights arranged within a much larger structure. The halo does not need to shine in order to determine where the stars can remain, how gas enters the system, or how neighboring galaxies respond. The relationship also changes across time. Dark matter halos were smaller. They merged repeatedly as cosmic expansion continued. Gas collected within them, forming early generations of stars. Some halos joined to build larger galaxies, while others remained as smaller companions, or were gradually stripped as they passed through denser environments. The galaxies we see today carry that layered history. The Milky Way is not only a disk of stars turning around a central region. It is also the result of earlier mergers, incoming gas, disrupted companions, and long gravitational interactions occurring within a dark matter halo. Streams of stars around the galaxy preserve traces of smaller systems that were pulled apart. Their paths can be used to study the mass distribution they move through. The halo itself may contain smaller concentrations called subhalos. Some may host faint dwarf galaxies. Others may contain few stars, or perhaps none at all. Their gravity can disturb stellar streams, alter gravitational lenses, or influence the motions of visible companions. Researchers look for these effects because they may reveal structure that produces little or no light. The dark matter framework is therefore not expected to be perfectly smooth. It has layers, concentrations, and remnants of earlier growth. A galactic halo may contain the gravitational memory of systems that merged long ago. What has vanished as a visible galaxy can remain partly present as motion, mass, and altered paths. On a clear night, the Milky Way may appear as a pale band across the sky. The visible glow comes from stars in the disk, mixed with dark lanes of dust. That band is only a narrow interior view. The galaxy's halo is thought to extend far beyond the luminous disk, surrounding the solar system and reaching into a region where the Milky Way's influence overlaps with the broader environment of its neighbors. You are not looking out from the edge of an isolated island of light. You are resting inside a moving galaxy, inside a larger halo, inside a filament of the cosmic web. The Earth turns beneath the sky. The sun continues around the galactic center. And all of that motion takes place within structures that began growing before starlight existed. The microwave background still arrives from every direction. Its photons have crossed most of cosmic history to reach this moment. They carry a faint image of early density patterns, while the galaxies around us show what those patterns became after gravity had worked for billions of years. One is the beginning of the map. The other is the map grown deep with time. Between them lies the hidden scaffolding that allowed small differences to become stars, galaxies, clusters, and the long-connected web stretching across the observable universe. The framework becomes more difficult to picture once we ask what the hidden matter is made of. Gravity reveals its presence across galaxies, clusters, and the early universe. But gravity alone does not provide a chemical label. A planet can be weighed from the motion of a moon without anyone knowing what lies beneath its clouds. Dark matter presents a far larger version of that problem. Its mass can be mapped, its influence can be measured, and its role in cosmic structure can be modeled. Yet, the substance itself remains unknown. The first possibilities were familiar ones. Astronomers once considered whether the missing mass might consist mainly of faint stars, failed stars, cold planets, black holes, or other compact objects that emit little light. These objects are real, and some certainly occupy galactic halo. A brown dwarf, for example, has too little mass to sustain ordinary hydrogen fusion. A lone planet between stars may be almost impossible to see. A black hole can carry great mass while producing no light unless matter falls near it. But a galaxy made mostly from such hidden ordinary objects would leave traces. When a compact body passes between Earth and a distant star, its gravity can briefly magnify the background starlight. This effect, called gravitational microlensing, allows surveys to search for dark objects in the Milky Way halo. The lens may never be seen directly. Its presence is inferred from the smooth rise and fall of the distant star's brightness. Years of monitoring showed that compact objects do contribute to the halo, but not in sufficient numbers across most plausible mass ranges to explain all of the missing matter. Other evidence points the same way. The early universe produced ordinary nuclei in proportions that depend on how much ordinary matter existed. The cosmic microwave background carries another measurement of that amount. Together, these observations indicate that most dark matter cannot be made from the same protons and neutrons that build stars, planets, air, and living tissue. The hidden component seems to require something outside the familiar inventory of atomic matter. That does not mean it must be exotic in a dramatic sense. It means only that nature may contain a kind of particle that interacts weakly with ordinary matter and light, while still contributing mass and responding to gravity. A useful candidate must satisfy several demands at once. It must be stable or survive for at least a large fraction of cosmic history. It must have been produced in the early universe in the right abundance. It must gather into halos and help form the observed cosmic web. It must avoid emitting, absorbing, or scattering too much light. and it must remain consistent with measurements ranging from underground detectors to colliding galaxy clusters. Many proposed particles fail one of these tests. A few broad families have remained especially important. One is the weakly interacting massive particle, often shortened to WIMP. The name describes an idea rather than one specific particle. In many theories, extending known particle physics, the early universe could have created heavy particles that interacted through forces comparable in strength to the weak nuclear force. As space expanded and cooled, most of these particles would have annihilated with one another. A residual population might have survived, leaving an abundance close to what cosmologists infer for dark matter. This apparent agreement once made WIMPs especially attractive. If they exist, they may pass through ordinary material almost without interruption. A great number could cross Earth every second without producing a noticeable effect. Very rarely, however, one might strike the nucleus of an atom and give it a small recoil. Direct detection experiments are built to notice that recoil. They are usually placed deep underground, where layers of rock reduce the rain of cosmic particles reaching the surface. The detector materials are chosen for sensitivity and purity. Liquid xenon, liquid argon, crystals, and other targets can be watched for tiny flashes of light, minute releases of charge, or traces of heat. The environment must be controlled with unusual care. Natural radioactivity in surrounding rock can imitate a signal. Materials used in the detector may contain faint radioactive contaminants. Neutrons can scatter from nuclei in ways that resemble the expected interaction. Even neutrinos, particles that are themselves elusive, can eventually become an important background as detectors grow more sensitive. The work is therefore built around subtraction. Researchers estimate every known source of noise, shield the apparatus, purify the target, and compare the remaining events with the pattern a dark matter particle might produce. A convincing discovery would need more than a few unexplained flashes. It would need a reproducible signal with the right energy distribution, the right behavior over time, and support from other experiments using different materials. So far, increasingly sensitive searches have narrowed the range of simple WIMP models. That result is not empty. A detector that sees no confirmed signal still teaches physicists which interaction strengths and particle masses are less likely. The search region contracts. Some once popular versions of the idea become difficult to maintain, while others remain possible. Dark matter may be heavier than expected, lighter than expected, or coupled to ordinary matter through a pathway. Current detectors are not designed to notice. Another major candidate is the axion. Axions were first proposed to solve a separate problem in particle physics involving the strong nuclear force. Later, researchers realized that very light axions produced in the early universe might also behave as cold dark matter. Unlike a heavy particle moving individually through a detector, axion dark matter could act more like a field spread throughout space, oscillating at a frequency related to the particle's mass. Experiments searching for axions often try to convert them into detectable photons in a strong magnetic field. The expected signal would be faint and narrow, more like listening for a single low voice buried inside the static of a broad radio band. The apparatus may tune through one small frequency range at a time, holding the conditions steady and waiting for an excess that cannot be explained by thermal noise or electronics. Because the possible axion mass spans a wide range, the search can be slow. Different instruments explore different frequencies. Some use resonant cavities, others use carefully arranged magnetic fields, quantum sensors, precision clocks, or condensed matter systems. The candidate is light, but the experimental challenge is substantial. There are also sterile neutrinos, hidden sector particles, ultralight fields, dark photons, and many other possibilities. Some models imagine that dark matter has its own set of interactions, almost like a shadow version of particle physics. It might contain more than one species. It might scatter from itself while rarely interacting with ordinary matter. It might form small structures or behave collectively across long distances. The phrase dark matter may therefore conceal variety. Ordinary matter is not one substance. It includes electrons, quarks, neutrinos, photons, atoms, molecules, plasma, ice, dust, stars, and planets. The visible universe is built from several particles and forces arranged in countless ways. There is no rule requiring the hidden sector to be simpler, yet a more complicated possibility must still earn its place through evidence. Particle accelerators provide another route. Instead of waiting for dark matter from the galactic halo to strike a detector, physicists collide known particles at high energies and search for signs that something invisible has been created. The unseen particle would escape the apparatus, but momentum in the collision should still balance. If visible debris appears to recoil against missing momentum, researchers can test whether an invisible product might account for it. This method does not detect galactic dark matter directly. It asks whether a particle with suitable properties can be produced under controlled conditions. Any promising signal would then need to be connected with astrophysical observations and direct searches. The same underlying particle should make sense in more than one setting. Astronomers also look for indirect evidence. If dark matter particles can annihilate or decay, they may produce ordinary particles such as gamma rays, electrons, positrons, or neutrinos. Telescopes search regions where dark matter should be concentrated, including galactic centers, dwarf galaxies, and clusters. The challenge is that ordinary astrophysical sources can create similar radiation. Pulsars, supernova remnants, black hole environments, and cosmic ray interactions all contribute backgrounds. An unexplained excess may be interesting, but it is not automatically dark matter. The sky is full of energetic processes. A persuasive interpretation must fit the shape, location, spectrum, and intensity of a signal, while surviving comparison with conventional explanations. This is why the search has continued for so long, without a single, decisive moment. Dark matter is not one experiment waiting to be completed. It is a meeting point between cosmology, astronomy, particle physics, nuclear physics, and precision engineering. Each field approaches the problem with different instruments and different forms of evidence. An underground chamber listens for a recoil. A radio frequency cavity listens for an axion. A collider measures missing momentum. A gamma-ray telescope watches the center of a galaxy. A stellar stream records a gravitational disturbance. A lensing survey maps mass across the sky. These efforts are not repetitions of the same test. They are different questions directed toward the same unseen component. Near Earth, the solar system continues through the Milky Way's halo. If dark matter is made from particles, they may be passing through the planet, now through the atmosphere, through the walls around you, and through the space between atoms. Most would leave no mark. That image can sound strange only because ordinary matter has trained us to expect contact. A hand rests on a surface because electromagnetic forces prevent its atoms from passing through the atoms below. Light reflects from objects because charged particles respond to electromagnetic fields. Dark matter, by definition, does not appear to participate in those exchanges in the usual way. It could occupy the same region without becoming part of the same texture. The search is an attempt to create one narrow point of contact. A nucleus shifts. A photon appears. A resonance rises slightly above noise. Nothing about such a signal would look cosmic at first. It might be a small cluster of events inside a carefully shielded instrument, recorded as numbers on a screen. Yet if the pattern held, it could connect a chamber beneath the ground with the halos of galaxies and the first growth of structure after the early universe became transparent. Until then, the candidates remain open. The gravity is clear enough to shape galaxies. The substance remains just beyond the reach of light. There is another way to approach the missing gravity. Instead of asking what invisible matter surrounds a galaxy, one can ask whether gravity itself behaves differently across very large distances or at very low accelerations. This possibility has remained part of the scientific conversation because the evidence for missing mass is indirect. Astronomers observe motion, lensing, structure, and the early universe. They infer that unseen matter is present because known gravity acting on visible matter does not appear to be enough. But an inference can sometimes point in more than one direction. Perhaps the matter is incomplete. Perhaps the law describing the motion is incomplete. The most familiar theory of gravity on cosmic scales is general relativity. It describes gravity not as a force reaching across empty space, but as the curvature of space-time produced by matter and energy. The theory has passed many tests, from the motion of planets to the bending of starlight, the timing of pulsars, and the detection of gravitational waves. Yet every theory is tested within a range of conditions. The gravity holding a person to Earth is strong compared with the acceleration experienced by a star near the edge of a galaxy. In those outer regions, the gravitational field is faint, spread across immense distances, and measured through motions that unfold over hundreds of millions of years. It is reasonable to ask whether a familiar law might change there. In the early 1980s, physicist Mordechai Milgrom proposed a framework called modified Newtonian dynamics, often shortened to MOND. The central idea was that below a very small acceleration scale, the relationship between gravitational force and motion might differ from the usual Newtonian expectation. Under ordinary conditions, the change would be negligible. In the weak outer regions of galaxies, it could become important. A star far from the galactic center might then orbit faster than expected without requiring a massive halo of unseen particles. The flat rotation curves that helped establish the dark matter problem could emerge from a modified rule of motion. This proposal was not made merely to fit one galaxy. It introduced a specific acceleration scale and produced testable relationships. One of its notable successes is the close connection between the amount of ordinary matter in a disk galaxy and the speed at which the outer galaxy rotates. Galaxies with more visible mass tend to have higher characteristic rotation speeds. The relationship is remarkably orderly. In many systems, the distribution of stars and gas predicts features in the measured rotation curve more closely than a simple picture of an independent, broadly distributed halo might suggest at first glance. Where the visible matter is concentrated, the rotation speed often responds. Where the distribution changes, the curve may show a related change. Supporters of modified gravity approaches point to these patterns as evidence that the motion of galaxies may be tied more directly to ordinary matter than the standard dark matter picture naturally implies. The question is serious because a good scientific explanation should do more than reproduce the broad fact that stars move quickly. It should explain the detailed shapes of rotation curves across many kinds of galaxies, bright spirals, small dwarf systems, diffuse galaxies with few stars, gas-rich disks, galaxies whose central regions are dominated by ordinary matter, and others where the missing component appears to dominate almost everywhere. MOND has shown an ability to describe many of these systems with relatively little freedom once the visible matter is mapped. That is one reason the idea has endured. But galaxies are not the only scale that matters. A complete gravitational theory must also count for galaxy clusters, gravitational lensing, the cosmic microwave background, the growth of the cosmic web, and the behavior of colliding clusters. It must remain consistent with the solar system and every smaller scale test that general relativity already passes. Here, that the challenge comes deeper. The original Mond proposal was not a full relativistic theory. It modified the relation between acceleration and gravity in a way useful for galactic motion, but additional work was needed to explain how light bends and how gravity behaves in a universe described by space-time. Several relativistic extensions have been developed. They introduce additional fields or more elaborate gravitational behavior, allowing the theory to address lensing and cosmology. Some can reproduce important observations. Others encounter difficulties or require additional unseen components of their own. Galaxy clusters remain a persistent problem. Even after modifying gravity, the visible stars and hot gas often do not provide enough mass to explain the full observed behavior. Some modified gravity models still need a hidden contribution, perhaps in the form of difficult to detect particles, such as neutrinos with particular properties. The amount and nature of that contribution depend on the model. This does not erase the value of the modified gravity idea. It reveals how demanding the full set of observations has become. A theory that works beautifully for one scale may struggle at another. The cosmic microwave background presents another test. Its pattern contains several characteristic peaks produced by oscillations in the early plasma. Their relative heights and positions depend on ordinary matter, radiation, the geometry of space, and the gravitational influence of matter that was not coupled to light in the same way. The standard cosmological model, including cold dark matter, reproduces this pattern with impressive accuracy across many measurements. Modified gravity models must recover the same early universe behavior without losing their successes in galaxies. Some approaches attempt this by adding new fields or particles. But as the framework grows more complex, the original promise of replacing dark matter with a simpler change to gravity can become less clear. Then there are colliding galaxy clusters. In systems such as the Bullet cluster, the hot gas slows during the collision while much of the lensing mass continues with the galaxies. A particle-like component that interacts weakly with itself and ordinary matter fits this separation naturally. A modification of gravity must explain why the inferred gravitational field appears displaced from most of the ordinary matter. There are proposed ways to address this, but the systems remain among the strongest challenge years to a universe containing no dark matter at all. The debate is not simply a contest between one idea that has succeeded and another that has failed. Both sides contain layers. The standard dark matter model explains the cosmic microwave background, large-scale structure, cluster dynamics, lensing, and the broad growth of galaxies, yet the identity of the particle remains unknown. On smaller galactic scales, simulations must include complicated processes involving gas, stars, supernovae, and black holes. The resulting predictions can depend strongly on how those processes are modeled. Modified gravity ideas capture several regularities in galaxy rotation with striking economy, yet extending them consistently across clusters, lensing, cosmology, and relativistic tests is difficult. The unresolved space between these strengths is scientifically useful. It encourages more precise observations. Astronomers study galaxies with very low surface brightness because ordinary matter contributes little to their gravitational field. They examine dwarf galaxies orbiting larger hosts. They map stellar streams for subtle disturbances. They compare the movements of stars, gas, and globular clusters far beyond luminous disks. Each system places pressure on the theories in a different way. Some galaxies appear to contain enormous amounts of dark matter compared with their stars. Others have been reported as possible examples with surprisingly little dark matter. though measuring their distances and motions can be difficult. If such systems are confirmed and understood, they may help distinguish between a separate material component and universal change in gravity. A dark matter halo can in principle be removed or altered through interactions with neighboring galaxies. A universal law of gravity cannot simply be stripped away. This makes unusual galaxies valuable, even when their interpretation remains uncertain. The motions of wide binary stars in the Milky Way have also been proposed as a test of gravity at low accelerations. Two stars, separated by a great distance, orbit one another weakly in a regime that may resemble the outer portions of galaxies. The measurements are delicate. Passing stars, unseen companions, and errors in velocity can affect the result. As the observations improve, these local systems may offer another path. The question can even be carried into the solar system, though any departure from known gravity must be very small here. Spacecraft tracking, planetary motions, and lunar ranging place tight limits on possible changes. A successful theory must become almost indistinguishable from ordinary gravity under these conditions. It must change only where needed. That is a narrow path. There is a comfort in science not requiring an early choice between competing pictures. The universe does not depend on our preference for particles or modified equations. It continues to move according to whatever is true, while observations gradually remove the possibilities that do not fit. A galaxy does not know whether its outer stars are held by a halo or guided by a deeper law. It simply turns. The stars trace their paths, the light reaches our instruments, and we compare each pattern with the worlds our equations describe. For now, most cosmologists work within a model containing dark matter because it connects a wide range of evidence with one broad framework. It explains how structure could begin growing early, why clusters contain so much unseen mass, how lensing maps extend beyond luminous matter, and why the cosmic microwave background has the pattern we measure. But the success of a framework does not make every question inside it complete. The small-scale distribution of dark matter is still studied. The behavior of galactic centers is still compared with simulations. The connection between visible matter and rotation remains unusually tight, and no detector has yet produced a universally accepted direct identification of the particle. Modified gravity remains a reminder to keep the original question open. Are we observing matter that does not shine? Are we observing a law that changes where acceleration becomes faint? Or could the final account contain elements of both, with new particles and a deeper understanding of gravity arriving together? The evidence does not yet permit every possibility, but it still permits more than one path. Across the night sky, galaxies continue to offer the same patient test. Their stars move through regions where the visible mass grows thin. Their outer gas follows broad, stable orbit. Their light bends around clusters and arrives from the early universe carrying a record of gravitational structure. Every measurement narrows the space. Every accurate curve removes another guess. And somewhere between the unseen substance and the law that guides it, the true architecture waits to be recognized. The largest structures of the universe make dark matter difficult to dismiss. The smaller ones make it difficult to understand. On the scale of galaxy clusters and the cosmic web, the standard picture works remarkably well. A universe containing cold dark matter naturally develops filaments, halos, and growing concentrations of mass. But when astronomers look more closely at individual galaxies, especially the smallest ones, the picture becomes more detailed. A dark matter halo is not expected to be perfectly smooth. Computer simulations suggest that large halos form through the gradual merging of many smaller halos. Some of those smaller structures are absorbed completely. Others survive as subhalos, moving within the larger gravitational environment like remnants of earlier stages in galactic growth. A galaxy such as the Milky Way should therefore be surrounded by many smaller concentrations of dark matter. Some contain visible dwarf galaxies, others may contain only a small number of stars. Many may contain no stars at all. This prediction creates a difficult observational problem. A starless halo cannot be photographed in the ordinary way. It has no bright center, no glowing gas, and no obvious boundary. Its presence must be inferred from the motion of something else. Dwarf galaxies provide one of the clearest places to begin. They are small systems containing far fewer stars than the Milky Way, yet many appear to be dominated by dark matter. In some of the faintest known dwarfs, the visible stars contribute only a small fraction of the total mass inferred from their motion. Astronomers measure the velocities of individual stars inside these galaxies. If the stars were held together only by their own combined mass, they should move within a limited range of speeds. Instead, they often move as though embedded in a much deeper gravitational potential. The galaxy may contain little light, but it is not gravitationally light. These systems are important because they offer environments where ordinary matter is relatively sparse. In a large spiral galaxy, gas cooling, star formation, supernova explosions, and central black hole activity can all reshape the inner distribution of matter. In a faint dwarf, there may have been fewer such events. The dark component can be easier to study when the luminous one has done less. Yet, dwarf galaxies are also difficult targets. They contain few bright stars. Their distances can be uncertain. Some are being disturbed by the Milky Way's gravity. Binary stars can complicate velocity measurements. A small number of unusual stellar motions can affect estimates of the total mass. Researchers must separate the internal motion of a dwarfed galaxy from the pull of the larger galaxy around it. Even then, the broad conclusion remains strong. Many dwarf galaxies appear to be rich in dark matter. The number of these systems has also become a major test of theory. Early cold dark matter simulations produce large populations of small subhalos around galaxies like the Milky Way. For a time, astronomers knew of far fewer dwarf galaxies than the simulations seemed to predict. This became known as the missing satellite problem. One interpretation was that the dark matter model was producing too many small structures. Another was that many small halos existed, but never formed enough stars to become visible. Star formation is not guaranteed simply because a halo is present. A very small halo may struggle to hold gas after the first generations of stars begin to shine. Ultraviolet radiation can heat the gas. Supernova explosions can drive it outward. The changing radiation field of the early universe can prevent gases from cooling into the smallest gravitational wells. A halo can survive while its chance to become a visible galaxy disappears. As sky surveys grew more sensitive, and astronomers found many additional dwarf galaxies around the Milky Way and other nearby systems. Some are so faint that their total starlight is less than that of a single large star cluster. The count is still incomplete. Parts of the sky are harder to search because of dust, bright foreground stars, or limited survey depth. Faint dwarfs may remain hidden at large distances within the halo. The number already known has reduced the original tension, though the relationship between predicted subhalos and visible galaxies remains an active field of study. The problem has changed rather than vanished. The question is no longer simply why so few satellites exist. It is which halos form stars, which remain dark, and how the earliest radiation and stellar activity determine the difference. Another challenge concerns the density near the centers of halos. Cold dark matter simulations often produce halos whose density rises steeply toward the middle. This is sometimes called a cusp. Observations of some dwarf and low surface brightness galaxies appear to favor a flatter central region known as a core. At first, This difference seemed like a possible sign that the dark matter model was incomplete. Perhaps the particles interact with one another. Perhaps they are warm enough to erase the smallest concentrations. Perhaps gravity behaves differently in weak fields. But ordinary astrophysical processes can also alter the center of a halo. When gas gathers toward the center of a young galaxy and then is driven outward by repeated bursts of star formation, the gravitational field changes. If this happens many times, dark matter particles moving through the region can gain energy and migrate into wider orbits. A steep central density profile can become flatter. The visible matter may be only a small part of the galaxy's mass, yet its repeated motion can reshape the dark matter nearby. This is one of the reasons small-scale questions are so difficult. The dark component and the ordinary component do not evolve separately. Gas falls into a halo. Stars form. Radiation heats the surrounding material. Supernovae move gas outward. The changing gravitational field alters stellar and dark matter orbits. The final galaxy contains the history of all these exchanges. A present-day density profile cannot always reveal which part came from the nature of dark matter and which part came from the behavior of stars. To separate those possibilities, astronomers compare many systems. A galaxy that formed stars in repeated bursts may develop a different center from one that formed very few stars. A dark matter model with strong self-interactions may produce cores even without energetic feedback. A warm dark matter particle may reduce the number of the smallest halos before galaxies begin to form. Each model leaves a slightly different population of structures. The work becomes a study of patterns rather than isolated examples. Stellar streams provide another kind of evidence. A stream forms when a globular cluster or dwarf galaxy is gradually pulled apart by the Milky Way. Stars escape along related orbits, spreading into a long, narrow ribbon that can wrap around much of the sky. The stars no longer remain in their original cluster, but they continue to travel together. A thin stream can act like a delicate gravitational sensor. If it passes near a dark subhalo, the encounter can disturb its structure. Some stars may be accelerated, others may be delayed. Over time, the stream can develop a gap, a bend, or a region of altered density. The subhalo itself may contain no stars. Its passage is preserved only in the changed arrangement of the stream. The difficulty is that other processes can produce similar features. The Milky Way's central bar, spiral arms, giant molecular clouds, and known satellite galaxies can all disturb stellar orbits. The stream's original formation history may also create unevenness. Researchers must reconstruct its path through a galaxy whose gravitational field is itself not perfectly known. Still, the possibility is powerful. A ribbon of old stars can record the passage of an object that never emitted light. Gravitational lensing offers a related method on much greater distances. When a distant galaxy or quasar is strongly lensed by a foreground galaxy, several images may appear. A smooth mass model predicts their positions and relative brightnesses. Small dark matter concentrations near the light paths can slightly alter those patterns. The result may be an image that is brighter, fainter, or shifted from what the smooth model expects. These small differences can reveal substructure in galaxies too distant for individual stars to be tracked. In some systems, the lens magnifies bright arcs whose detailed shape can be analyzed. A dark subhalo near the arc may produce a localized distortion. As observations become sharper, astronomers can search for smaller and smaller perturbations. The method does not require the subhalo to form stars. It requires only gravity and a well-placed background source. Together, dwarf galaxies, stellar streams, and gravitational lenses turn the smallest structures into tests of the dark matter particle. Cold, weakly interacting, dark matter tends to preserve abundant small halos. Warmer particles can move out of small density variations and suppress structure below a characteristic scale. Self-interacting dark matter can redistribute mass inside halos and alter their central densities. Ultralight fields may resist forming structure below scales related to their wave-like behavior. The smallest galaxies are therefore not small questions. They sit near the boundary where cosmology, particle physics, and the complicated life of ordinary matter meet. A mismatch does not immediately identify the cause. A missing dwarf may never have formed stars. A central core may have been shaped by supernovae. A gap in a stream may come from a molecular cloud. A lensing anomaly may depend on the foreground model. But as the number of observations grows, accidental explanations become harder to sustain across every system. Patterns begin to separate. The Milky Way's halo is likely filled with remnants of earlier assembly. Some are visible as companion galaxies. Some survive as dark subhalos. Some have been stretched into streams. Others have merged so thoroughly that only their gravitational contribution remains. The galaxy carries them without displaying them. Far above the luminous disk, faint stars move along extended paths. Small galaxies orbit within the larger halo. Narrow streams preserve encounters that may have happened long before human beings began mapping the sky. These structures are not static. They are crossing, dissolving, and being absorbed. The hidden architecture has its own history. By studying its smallest surviving pieces, astronomers are trying to determine whether dark matter is cold, warm, self-interacting, wave-like, or something not yet placed into any familiar category. The answer may not first appear as a particle striking a detector. It may emerge from the number of dwarf galaxies, the width of a stellar stream, or a slight distortion in a distant arc of light. On these scales, the universe speaks through imperfections. A gap where stars should have continued. A galaxy held together by more mass than it shows. A lens whose image cannot be explained by a smooth halo alone. Each irregularity is small. Together, they trace the texture of the unseen. There is a point in this search where the instruments begin to feel almost secondary. Not because they are unimportant, but because each one is listening for a different kind of answer. A detector beneath rock waits for a collision. A telescope measures the bending of distant light. A survey follows the motions of stars. A simulation allows gravity to work across a model universe and asks what structures emerge. No single method can carry the entire question. Dark matter sits between fields that usually speak different technical languages. Particle physicists describe interactions, masses, and symmetries. Astronomers describe halos, rotation curves, and lensing maps. Cosmologists describe the growth of structure and the statistical pattern of the early universe. The same unseen component must make sense in all of them. This creates an unusual form of patience. A candidate particle may be elegant on paper, but fail to produce the right galaxies. A model may reproduce galactic motion, yet struggle with clusters. A simulation may build the cosmic web successfully while leaving unresolved questions near the centers of dwarf galaxies. An unexplained signal in a detector may disappear when a background source is understood more carefully. The search advances not only through discovery, but through removal. Each failed candidate narrows the field. Each null result closes part of the map. Each improved observation makes the remaining possibilities more specific. Scientific progress is sometimes imagined as a sequence of bright moments, but much of it is closer to erosion. Explanations are tested again and again until their weak edges wear away. What survives becomes harder, smaller, and more precise. Dark matter has endured that process for decades. The evidence for missing gravity has grown broader. The list of possible substances has changed. The standard cosmological model has become more detailed. Detectors have become quieter. Surveys have mapped larger volumes. Simulations have gained more resolution and more realistic descriptions of ordinary matter, yet the central object remains unseen. This absence can feel like a gap, but it is also a shape. Dark matter cannot interact strongly with light, or it would not remain dark. It cannot behave like ordinary gas, or cluster collisions would look different. It cannot be made mostly from familiar atomic matter, or the early universe would carry another pattern. It must gather gravitationally, persist across cosmic time, and allow galaxies to form in something close to the way we observe. The unknown is not without boundaries. It occupies a narrowing region defined by everything it has failed to do. That may be one of the deeper lessons hidden inside the subject. Knowledge does not always begin with seeing the thing itself. Sometimes it begins with noticing the paths around it. A planet was once inferred from the motion of another planet. A black hole can be studied through nearby stars and heated gas. The interior of Earth is known through waves passing through it. In each case, the hidden object becomes measurable because it changes something that can be observed. Dark matter extends this principle across the universe. Its strongest evidence is relational. A star moves too quickly. A galaxy cluster holds together. A background image bends. A density pattern grows. A stellar stream develops a gap. None of these effects belongs to dark matter alone. Each must be separated from other possibilities. But together, they form a network of consequences, too broad to ignore. There is something deeply human in learning through consequence. You rarely see gravity itself. You see falling rain, orbital motion, the curve of a thrown object, the tide rising along a shore. Gravity enters experience through what it changes. Dark matter is even more removed. It does not announce itself through touch, color, warmth, or sound. It enters knowledge through the motion of systems so large that no person could ever watch one complete an orbit. A star near the edge of a galaxy may require hundreds of millions of years to return to the same place. Human astronomy samples only a fraction of that path. Still, motion leaves enough information. A shift in wavelength reveals speed. A distribution of speeds reveals mass. A pattern, repeated across galaxies, reveals a larger rule. The scale of the inference is immense, but the measurements begin with small changes in light. There's an older thread running through this work. For most of human history, the night sky offered orientation. The repeated rising of stars helped travelers and sailors hold direction when the ground or sea provided few signs. The sky was valuable because it appeared stable. Modern astronomy uses that stability in another way. Distant galaxies become reference points. Background stars become markers. A narrow stream becomes a ruler laid across the halo. Light from the early universe becomes a record against which later structure can be compared. The same sky that once helped people cross oceans now helps scientists map matter that cannot be seen. The purpose has changed, but the act remains recognizable. You begin with what holds steady, then you notice what has shifted. A scientific map of dark matter is therefore not an image in the familiar sense. It is a reconstruction. It is assembled from positions, shapes, motions, and statistical relationships. It may appear as a colored field, spread across a cluster or a broad region of sky, but the colors are not the colors of the matter itself. They are a language for gravitational influence. This distinction matters. Dark matter is often represented as smoke, mist, blue light, or a translucent web. Those images are useful, but symbolic. The real substance, if it is a substance, may have no visual appearance at all. A person could move through a dark matter halo without seeing a veil. A spacecraft could cross a dense region without encountering a cloud in any ordinary sense. The halo would reveal itself only through gravity or through an interaction so rare that current instruments are still waiting for it. Its reality may be physical without being sensory. That is difficult for the mind because human understanding grew around surfaces, sounds, textures, and light. Matter is expected to resist, reflect, heat, cool, break, or combine. Dark matter seems to participate in almost none of those familiar exchanges. It may share space with ordinary matter while remaining largely detached from ordinary experience. And yet the visible universe may owe its form to that detachment, because dark matter did not remain coupled to radiation. In the same way as ordinary matter, it could begin gathering early. Because it does not appear to lose energy through light, it forms broad halos rather than thin disks. Because it interacts weakly, it can pass through colliding clusters while hot gas slows behind. Its elusiveness may not be an accidental inconvenience. It may be the reason it shaped the universe in the way it did. If dark matter interacted more strongly, galaxies might have formed differently. Halos might have collapsed into other structures. The cosmic web might have developed another texture. The night sky, the Milky Way, the solar system, and Earth all arose within the particular history allowed by matter that barely touched light. The hidden component is not only missing from our detectors, it is present in the conditions that made those detectors possible. Every laboratory rests on a planet formed inside a galaxy. Every galaxy formed within a larger gravitational environment. Every researcher looking for dark matter is already inside the structure being investigated. There is no distant shoreline from which to study it. The solar system travels through the Milky Way's halo, while instruments measure the possibility that halo particles are passing through them. Telescopes inside one galaxy observe lensing produced by another. Minds built from ordinary matter try to infer a component that may outweigh ordinary matter across the cosmos. The search folds back on itself. You are not outside the problem, you are carried by it. The bed beneath you, the building around you, the city beyond it, and the turning Earth all move through the galaxy together. The motion is smooth enough to disappear from daily awareness. There is no wind from the halo, no visible stream crossing the room. Only the larger orbit continues. This present moment is already taking place inside dark matter's inferred domain. That thought does not require certainty about the particle. Even if the final explanation changes, the measured motions remain. Galaxies rotate as they do. Clusters bend light as they do. The early universe left the pattern it left. Any future theory must return to these observations and explain them at least as well. The name may change. The equations may deepen. The hidden architecture may turn out to be one particle, several particles, a field, a change in gravity, or a combination not yet imagined. But the sky has already given the conditions of the answer. It must hold galaxies without shining. It must shape structure without becoming visible. It must leave almost no trace in the hand, yet write itself across billions of light years. For now, the search continues through careful measurements and increasingly narrow possibilities. The darkness between stars is not empty. The spaces around galaxies are not without form, and beneath every luminous system, gravity continues to describe what light has not yet revealed. The search now reaches a boundary that is not marked by distance. It is marked by what can be known before a direct detection arrives. Dark matter may surround the Milky Way, shape the motion of nearby dwarf galaxies, and extend far beyond the visible edge of every large galaxy. It may form the hidden mass of clusters and the deeper pattern beneath the cosmic web. Yet its identity remains outside the reach of any single observation. The next step could come from almost anywhere. It may begin in a detector shielded beneath layers of rock, where one unusual collision survives every test for contaminations. It may appear as a faint, repeating signal inside a resonant instrument. It may emerge from a gravitational lens whose distortions reveal that dark matter has structure on a scale no existing model predicted. Or the change may be quieter. A larger galaxy survey may map millions of tiny lensing distortions and show that halos grow differently from present expectations. A stellar stream may contain several gaps whose arrangement points toward a specific population of unseen subhalos. A dwarf galaxy may preserve a central mass distribution that cannot be reproduced by ordinary stellar processes alone. The discovery does not need to arrive as a dramatic flash. It may begin as a small inconsistency that refuses to disappear. That is how many deep changes in science first take shape. A measurement is repeated, an instrument is improved. The uncertainty becomes smaller, but the mismatch remains. Different teams approach it from different directions and find the same outline. Eventually, what once looked like noise becomes information. A direct particle signal would not end the story. It would begin a more detailed one. Physicists would need to measure the particle's mass, its stability, and the strength of its interactions. Astronomers would ask whether those properties produce the halos they observe. Cosmologists would test whether the particle behaves correctly in the early universe, and whether it creates the right abundance of small structures. One detection would have to connect with many skies. A particle created in a laboratory would need to be the same kind of matter shaping. Galaxies billions of light years away, a signal recorded over a few seconds would need to fit structures that have evolved for most of cosmic history. The scale of that connection would be difficult to match anywhere else in science. A tiny event inside a detector could explain why stars remain in orbit around distant galactic centers. A narrow frequency peak could reveal what helped build the cosmic web. A pattern of missing momentum could point toward the material surrounding the solar system at this moment, but another path remains possible. The growing evidence may reveal that the phrase dark matter has been covering more than one phenomenon. There may be several particles, several interactions, or a mixture of hidden matter and gravitational behavior not yet fully described. Nature is not required to offer one simple substance merely because one simple name has been useful. The visible universe already contains many forms of matter. Hydrogen clouds, iron cores, plasma, dust, planets, stars, and living cells all arise from a small set of known particles arranged under different conditions. A hidden sector could also contain structure, even if its interactions with ordinary matter are weak. Some of it may gather smoothly. Some may form compact concentrations. Some may decay over timescales longer than the present age of the universe. Some may leave traces only in the smallest galaxies or the earliest patterns of cosmic structure. The term dark matter may survive as a broad category even after its contents become known, or it may eventually be replaced. Scientific names often begin as placeholders. They describe the location of a problem before the mechanism is understood. The name remains useful because it points toward a consistent absence. Gravity is present, while light is not. Whatever replaces that absence must explain the full record. It must account for galaxies whose outer stars move too quickly for visible matter alone. It must explain clusters whose total mass exceeds their luminous content. It must reproduce gravitational lensing across wide regions of sky. It must fit the early microwave background and the later growth of cosmic structure. It must also survive the careful tests provided by dwarf galaxies, stellar streams, colliding clusters, and laboratory experiments. The answer will not be accepted because it is imaginative. It will be accepted because it keeps working. Until then, the uncertainty remains part of the science rather than a failure of it. There is a difference between not knowing and having no direction. Dark matter is unknown in composition, but it is constrained by decades of observation. Its possible behavior is surrounded by limits. Its influence has been measured in several independent ways. The remaining space is smaller than the word mystery might suggest. We do not stand before a blank universe. We stand before a detailed pattern whose source has not yet been named. That pattern is already enough to change how a galaxy is understood. The bright disk is not the whole system. The spiral arms do not mark the true edge. The last visible star does not indicate where the gravitational structure ends. Beyond the familiar light, the halo continues outward, becoming thinner and broader, meeting the environment of neighboring galaxies and the larger filament in which the system formed. The galaxy is both luminous and hidden. Its stars provide the image. Its unseen mass provides much of the shape. For a listener beneath the night sky, none of this changes what the stars look like. The constellations remain points of light. The Milky Way, where it can be seen, remains a pale band across the darkness. Nearby galaxies still appear as faint smudges through a telescope, but the meaning behind those lights has widened. Each galaxy is surrounded by more than its image reveals. Each cluster carries more mass than its glow suggests. Each broad, empty region sits beside filaments, whose structure grew from early differences in density, guided by gravity across billions of years. The visible universe becomes less like a collection of isolated lights and more like the illuminated portion of a much deeper design. There is no need to picture dark matter as smoke or shadow. It may have no appearance that human vision could recognize. It may pass through ordinary matter without forming a surface, a color, or a cloud. Its presence is better imagined through motion. A star follows an orbit. A galaxy bends distant light. A cluster holds together. A filament gathers galaxies along its length. The hidden component is written into those paths. And perhaps that is the most fitting way to leave it tonight. Not as an object waiting to be seen, but as a pattern already moving through the universe. Long after this moment, stars will continue circling their galactic centers. Small galaxies will continue falling through larger halos. Clusters will merge. Light from remote sources will cross curved space-time and arrive, carrying the outlines of mass along its path. Some future observer may know the particle's name. They may understand its origin, its interactions, and its place within a larger theory. What seems hidden now may become part of an ordinary scientific description, taught with the same ease as atoms, gravity, or starlight. Yet the galaxies will look much as they do tonight. Their luminous forms will still be only part of what they are. The unseen will keep holding the light in motion.